continue our journey here a little bit. Next section is 1.6 about the graphs of functions. I'm just going to lead us through some parts of the book and maybe give a little extra explanation of what's there. This first thing they call the fundamental graphing principle for functions. That when you see something in a box like that, that's usually considered by the authors at least to be something important. It sounds a little vacuous, I have to say, but what they're basically doing is trying to tell you that the graph is a set of points, and the points satisfy the equation. So if you have y equals f of x, well, if you have a function f of x, and then you create the relation y equals to f of x, you get a point x comma y on the graph precisely when the y coordinate is equal to the function applied to the x coordinate. So they ask us to do an example here. Graph f of x equals x squared minus x minus 6. Let me do some writing here to illustrate how you might go about this. Now, this is how you might go about it by hand rather than how you do it with a calculator or technology. But I would make myself a little chart of x values and y values first. I mean, that's a step to take. I'm going to start a little bit down low because I want to begin with the x value of 0. I'm going to go back up a little bit into negative values, but also down into positive values from there. Now, the graph, the function rather, is x squared minus x minus 6. Probably should have written that on my page. So choosing to get a value for when x is 0, that's, well, a particularly easy one to do, isn't it? The value when x is 0 is just readable from this equation. You see, when x is 0, the x squared is 0, and the x is 0, you just get the minus 6. Okay? So we know that the y coordinate that goes with the x coordinate of 0 is minus 6. Let's go to some nearby things, minus 1 and plus 1. When x is 1, what do we get out of this formula? Well, 1 is kind of nice because 1 squared is 1, and x itself is 1, right? So that's 1 minus 1, or 0. Oh, we get minus 6 again, don't we? Does the same thing work for minus 1? That's a little different. Minus 1 squared is 1, but then we're subtracting minus 1, which means you're adding 1. So you get 2 minus 6, which is 4. No, negative 4. Well, let's try to move up again a little bit. What if we have x is equal to 2? Again, this is one you could probably do just in your head. 2 squared would be 4, and then minus 2. 4 minus 2 is 2, and then minus 6. Oh, negative 4. Now, I'm starting to notice a nice little pattern. There's sort of 0 and 1 have the same value, 2 and minus 1 have the same value. Maybe I only have to figure out one of a pair of things and the other one will follow from it. What do you get if you stick 3 into this formula? 3 squared is 9, minus 3, that's 6, and then minus 6 minus 6. Not 0. The position that comes back here would be negative 2. Does that also give us 0? Tough one to see. Minus 2 squared is 4, and then we're subtracting minus 2. 4 minus minus 2, 4 plus 2, 6 again. Oh, and 6 minus 6, 0. So what I've done there is produce a list of points, really. I made it as a table, but each one of these rows in the table is a point, an x coordinate and a y coordinate, and we can plot them. I'll go ahead and do that now. Make an xy axis. We've got values for x's minus 2, minus 1, 0, 1, and 2. Oh, and 3. a little farther in the plus direction than I did in the minus. The y coordinates, excuse me, that are easiest to plot are the ones where it's 0. So when x was minus 2, we have a 0. And when x was plus 3, we have a 0. Let's see. Another one that's easy-ish to plot is when the x coordinate is 0, the y coordinate is minus 6. I'm going to drop down here 6 units below the axis. I guess my y-axis wasn't quite long enough. Let me stretch it some. I just noticed I was being sort of bad. You're supposed to label the axes and put the arrows on the ends of them. I didn't do that. Okay, so when 0 is the x coordinate, negative 6 is the y coordinate. And what else did we have? Minus 4, that height, when we're at negative 1. Also, when we're at plus 2, we get that minus 4 value. Those look like they're the same height. Good. And then we had a value of minus 6 when we're at plus 1. So now I've got 6 or 7 points here. 6. And I could kind of connect the dots and draw it, but I want to caution you against something. A lot of people will connect the dots by drawing straight lines between these things. But this is not a whole bunch of straight lines. You should try to connect the dots in a smooth way. There's a curve that goes through all these points, not a line, or not a sequence of lines. So don't make it look, I don't want to show you what not to do. Let me show you what to do. Try to make a smooth curve that goes through these points. Well, get as close as you can as going through the points. That curve is a parabola. It's a kind of graph you probably have seen before. Let's just drop the doing it by hand part and show you how you would do that in Desmos. Well, it's a whole lot easier. You don't have to write y equals. You just can put in the formula, x to the second. I'll give you a little hint about Desmos. If you just type in x to the second, and then you say minus x, and then, was it minus 6? That worked. Huh. I was going to tell you that that wouldn't work. There are times in Desmos when you put yourself in the exponent and then you get stuck in the exponent, but this time it understood it. I think they must have made some recent improvements to the program because it's doing what I wanted as opposed to what I was afraid it would do. Yeah, that's strange. Now I'm trying to figure out, what if I wanted it to say 2 minus x up in the exponent? How could I get that to happen? Oh yeah, sure, I could use parentheses and make that happen, so never mind. Good, thank you Desmos, you've improved the product, that's great. So, do you see the graph that we've got here? You don't see all the points that we found over on the written page I was looking at there. But what Desmos is doing is actually plotting probably thousands of points in here. And it, in fact, is probably connecting them with straight lines. But those straight line segments are so ridiculously short that you don't see it. It looks like a nice smooth curve. They are highlighting some of the points, though, that we see here. And the ones I want to concentrate on right now is not this one that I clicked, but those 3. Those are called the intercepts. And those are usually some points that it's fairly easy to compute, and so it's kind of a good idea to do them. Often if you kind of know what the shape of the curve is and also what the intercepts are, you can sketch it without having to do a whole bunch of points. That is, these 3 would actually be pretty much enough to draw the whole graph. If in addition I had that one that's at the low spot at the bottom there, that really nails it down. I know what a parabola that has those 4 points on it is going to look like, so I can sketch it quickly. There's another example in the book that we should take a look at. This one is a little tougher because they have a function that's defined in a pointwise fashion, a piecewise fashion. So what I'm looking at here is example 1.6.2. You're graphing 4 minus x squared if x is a below 1, and x minus 3 if x is greater or equal to 1. Let me do this first by hand, and then again we'll see how to do it using the technology. So to do it by hand, maybe I should first copy what I need to copy onto my page here. 4 minus x squared is what we need when x is less than 1, and x minus 3 if x is greater or equal to 1. Those two things together are the definition of f of x. Yeah. All right, so let me bring this back to the 4. Well, basically what I'm going to do is lightly draw in both of these graphs. And then stitch them together is the way I refer to it, using these two intervals on which the separate parts of this function are going to be defined. So well, let's start at the bottom. What does x minus 3 look like? That's pretty easy to graph. If you should remember doing the graphs of linear equations before. It has a y-intercept at minus 3. So when x is 0, you get minus 3. And it's got a slope of 1, because it's just x, right? There's no multiplier out in front of it. So that means we go over 1 and up 1, over 1 and up 1 from there. And another way to say it is we travel along the slope, a line of at 45 degrees. So that's what x minus 3 would look like. What does 4 minus x squared look like? Well, when x is 0, that has a value of 4. And when I subtract x squared, it's like it gets you an upside down parabola. We'll see how to do this kind of thing in much more detail later. But for now, if you don't know this, it's not a big deal. You could use something like a calculator or Desmos to figure it out. Okay. So wow, I've got those two graphs, but that's not really what I want. Well, for instance, what I've drawn so far isn't a function. Do you see how there are vertical lines that would hit the pair of these things twice? So what I need is a single graph that does what we want. That while our x coordinate is less than 1, will be on the parabola graph, and when we're greater than or equal to 1, will be on the x minus 3 graph. Let me do that part first. X equals 1 is about right there. So if we're on the part of this line that we're supposed to be on, I should use a different color. Excuse me. The part of the line that we're supposed to be on is from here to the right. I'm going to make it nice and bold and red so we can see it nicely. Actually, the color doesn't seem to come out very well through this webcam. But trust me, that's red. Does it work better if I'm a little bit larger? Not really. Okay, so that's fine. When we're less than 1, we're on the parabola. So x equals 1 on the parabola would be right about, I think it's right about there. That point, though, is not on the parabola. You have to be less than that point. Nevertheless, you sort of draw it, make an open circle around that point, and then cover the parabola with red everywhere to the left of the point that I just did. Okay, let me try to make it sort of bold so we see it better. So this graph is kind of an oddball. Do you notice what happens? You travel along this nice smooth parabola, and then suddenly you teleport down to -2, and then you follow a straight line. So it's got a jump in it. That's something that physically is often very unrealistic. You know, a thing can't move in a path like this where it follows a parabola and then suddenly jumps over here, unless you're thinking of quantum teleportation. But there are things that do change in a jump like that. For instance, a tax rate. You know, it's one number up until you make $100,000, and then it's a totally different number beyond that. So there are times when we do have graphs that are functions that make perfect sense, that have this kind of feature where there's a skip or a jump in them. It's called technically a discontinuity. All right, let's return to doing this in the modern era and look at what it would be like to do that on Desmos. Did I kill the window that had Desmos in it? There it is. Okay, so let me do the two pieces separately. We had 4 minus x squared. Okay, that's this downward curving parabola. And we also had the graph x minus 3. So at this stage, I'm kind of like what I did originally on the paper. I just have the two graphs, but I don't have them together as one does one part of the function and the other does the other part of the function. One thing that's an element of that is I kind of like them to be the same color. So I'm going to change this guy to color red. Both things are red now. The other thing, though, is that I want to only draw this parabola when we are less than 1. And you can do that in Desmos the following way. After the function definition, you can specify the domain. You put a curly brace to indicate that it's that it's a set. The set of x coordinates for which we're going to draw this graph. And what we want is x less than 1. Just put in that inequality, and that's what it draws for you. What was the domain we wanted for the other graph? That would have been x greater than or equal to 1. So there I've gotten Desmos to draw the graph in a pretty reasonable way. I'm actually not completely happy with this representation. Desmos isn't indicating the difference between the point I'm indicating right there should be a solid point, and the point up here should be an open point. It's not showing that. So you could do that by hand. You can tell it to plot a point by simply naming the coordinates of the point. So this one on the parabola is 1, 3, isn't it? I'm not liking that it's red, and I'm not liking its style. So I'm going to turn it. That was weird. I said red, but what I meant is green. It's not green. It is green, and I don't want it to be green. I want it to be red. And then the other thing you can get when you've gone into the style menu here is change it to an open circle. That looks better. And then the other point, the point that's included on the graph, as opposed to this point is excluded from the graph, would be, what is this? 1, minus 2. It's drawn it in purple. It just always cycles through the thing. So I think I did this without saying it. There's a gear symbol up here. That's how you get to make changes to the styles of things. Click on the color and turn it to red. It's already it's their style. So that is a solid graph of what it looks like, of what this function, this piecewise defined function is supposed to look like. A little bit of extra work. I would have probably been fine with it if we just did these first two things, but I thought I'd show you how to get the points to kind of look right if you want to go to that trouble. Okay, so back to the book here. The next piece of information I want to get is, again, look for these boxes. They tell you the important things that we're after. Definition 1.9 here, the zeros of a function. In the old days, people called these roots of a function, which it had something to do with thinking about taking square roots to solve quadratic functions, but or higher order roots for higher order functions. You may still hear people, particularly old people like me, say roots when they mean this concept, but it's much more, the more modern and accepted terminology is zeros. So the zeros of a function are solutions to where does the function equal 0? Well, it's kind of like the name says. So a particular, I kind of hate that we're simultaneously using x as a variable and as a particular number, but a particular x value is a 0 if and only if the point x comma 0 is an x-intercept, or you could say it is x gives you a solution to f of x equals 0. So on this, what are the zeros of our function? Desmos is pretty good about it. If you click on anywhere near the 0, it'll kind of jump to it. So minus 2 comma 0 is a x-intercept, but the 0 is just the x value of that, minus 2. And the other one, there it is. 3, 0 is the x-intercept, but 3 is what we would call the 0. I think that's pretty easy. Not such a big deal. There's some stuff. The next big box to look at is talking about symmetries on a graph. And you'll notice that they talk about two kinds of symmetries here. There's 2 bullet points in here. Symmetry about the y-axis and symmetry about the origin. So I think that requires a little bit of graphical explanation. They've done it with a formula there, but let's talk about it in terms of a graph. If I have a couple of points that are exactly across from one another across the y-axis, this is the y-axis, this is the x-axis, that's what I mean by symmetry across the y-axis. So suppose this one was 2, 4. What is this other one that's exactly across from 2, 4 across the y-axis from 2, 4? Well, it's going to have the same height. So its y-coordinate is 4. And its x-coordinate, well, it has to actually be the negative of the x-coordinate of this one, doesn't it? It's minus 2, 4. And that's the idea in general. If you have a bunch of points that are across from one another, you'll get something that's symmetrical around the y-axis. You may have some points that are literally on the y-axis. Excuse me. But what I was trying to draw was a graph that's symmetrical around the y-axis. A little bit weak there, isn't it? There's a lot of graphs we can do that are symmetrical around the y-axis. And you'll see that they have this property that for every x, for every value of x, maybe we should say, for every x value, f of x and f of minus x are the same. What it's saying is if I've got one of these graphs that has this sort of symmetry, if I go over to the right x units and up to the graph, I'll get the same thing as if I go over to the left x units and then up to the graph. You see that those points are at the same height. Well, that's what they've said in an equation right here. F of negative x equals f of x. Sorry, that's hard to highlight and make it look right because of the math mode. Wow, look at the equation they've written for the other kind of symmetry, the symmetry they call about the origin. F of negative x is the negative of f of x. Wow, what's that saying? Well, first, let's look at what it would mean for points to be symmetrically placed around the origin. The origin is this spot. If I have a point up here, let's stick with 2, 4. To be symmetrically placed around the origin means sort of you would travel down to the origin and then keep going in the same direction, the same amount of distance you just did, and find a new point. So where is that new point located? Well, we've made the x-coordinate be the negative of the previous x-coordinate. We've also made the y-coordinate be the negative of the y-coordinate. So that's minus 2, minus 4. The x-coordinate is the negative of its symmetrically placed friend, and the y-coordinate is the negative. So if you did this more generically, you'd have a point x comma y, maybe out in the first quadrant. The thing that's symmetrically placed, I think that looks roughly symmetrical, doesn't it? Yeah. Anyway, it would be minus x comma minus y. Well, this thing they've written in here accomplishes that. That the value at negative x that's the y coordinate, negative x, is the negative of f of x. That's the y coordinate at x. So this is the y coordinate of the point to the left is the negative of the y coordinate to the point to the right, or vice versa. The y coordinates are negatives of one another, and clearly x and minus x are negatives of each other. So that gets you that sort of symmetry around the origin. The deal, though, is we want that to be the case for every x value. For every x, f at x and f at minus x are negatives. I guess I better write it the other way. F of minus x and f of x are negatives of each other. One has a minus sign, the other doesn't. You could put both minus signs over here, right? It kind of doesn't matter. Multiply that equation through by minus 1, and then you'd have f of x equals negative f of negative x, but that feels like piling on minuses on one side. Okay, so there's some words used in here, even and odd, and those are normally reserved for numbers, right? We say a number is even if it ends in 0, 2, 4, 6, or 8. An odd is the other numbers ending in 1, 3, 5, 7, or 9. What we mean by functions being even or odd is that they have one or the other of these two kinds of symmetries. And I think that requires a little explaining. Let's kill off some of this stuff, and I want to draw for you some graphs that have x to powers, like x to the even number 4. What kind of power, what kind of symmetry do you see on this graph? Hopefully you see its symmetry across the y-axis. A point here and a point here have the same y-coordinate. So they have negatives of the x. You know what, I can actually draw these points. Let's do, let's call it k and k to the 4th power. And we'll add a slider for k. And now I can use the slider to move that k around. I think that's a terrible span that the default for the slider is. How about we go from 0 to 2 is plenty. Oh, I just said 2 and typed 3. 2. So now I can use the slider to move pretty much on the part of the graph we're seeing. Okay. If I wanted to, at the same time, have a point that was on the other side of, that is to the left of the y-axis, the coordinates would be, well, actually minus k and minus k to the 4th. I wrote that in a kind of a goofy way, but do you see that these guys are always sort of mirror images of one another across the y-axis? Let me point out that this way of writing it, minus k to the 4th, is a little bit dense. I mean, I was just saying I want to sort of make it be on the graph, right? But what is the value of minus k to the 4th? You'd have this negative sign times k, or minus 1 times k, raised to the 4th power. That's 4 copies of minus 1 multiplied together, which is plus 1. So really, I didn't need that. I could have just said k, minus k and k to the 4th, and I'd get the same result. Let me show you that it makes no difference. Now, it's kind of fun to see that you can algebraically simplify, and it's all good. So yeah, this is the kind of symmetry where we talk about symmetry across the y-axis. And that came from a graph where we had x to an even power. If I replace that 4 up there with another even number, how about minus 2? There's an even number. Well, I got to replace these 4s with minus 2s as well. And I may have to mess with the range of the graph, the slider, but again, we've got that symmetry of things that have negative x coordinates of one another have the same y coordinates. mirror image through the y-axis. And it turns out that every even power that I might want to stick up there on the x gets me a graph with this sort of symmetry. So they make a definition from there that if you have a graph with this across the y-axis symmetry, call the function even. What happens if we try an odd number? Let's just do that. I'm going to put in 3's. Whoops, I got a subscript 3. And I don't know why that turned into a subscript, but I think I was just sloppy. No, I got really sloppy. I didn't see it on that one. X to the third power. And now, now it matters. K cubed and minus k cubed are different numbers because of this being an odd number. So I really can't do the simplification I did before. I do have a minus sign in there. Now what's going on with these pairs of points that are sort of symmetrically placed across the origin, on the x-axis, right? One has a positive x-coordinate, the other has a negative x-coordinate. And they're both on the graph of k cubed, or of x cubed, if I were to say. But you see that these guys are mirror images through the point, the origin, rather than across the y-axis. Mirroring in a point is a strange idea, but there's really a line that goes from that point to the origin, and if we move in the same direction, we'll end up at this point. And the distances from the origin out to the red point is the same as the distance from the origin out to the green point. That's symmetry in the origin, and that came about when we had an odd power. And believe me, if you stick any odd exponent up here, you're going to get the same kind of symmetry. It'll look entirely differently, but the symmetries are the same. Let's just do a minus 1 to bring that point home. Minus 1's an odd number. Turn these guys all into minus 1's as well. Strange looking graph. It's called a hyperbola. But you see the symmetrically placed points on the graph, and if I change the slider, they move. Well, they go off to infinity and minus infinity right up there. That's not cool, but you know, staying away from 0, they move symmetrically around the origin. So again, this is the x-coordinates are negatives and the y-coordinates are negatives, or as they put it in the book, you pull a f of minus x is the same thing as the negative of f of x. Okay, one last topic to talk about in this section, and this is about sort of the gross behavior of graphs. They do some more examples of it, but I don't want to beat you to death with examples. Come on, general function behavior. Okay. These are pretty easy concepts. Increasing, decreasing, and neither, constant. And they've given a graph that's got a piecewise definition here, but we don't need to worry about the piecewise, just look at the picture. There are places where it's going up, places where it's going down, and places, like right there, in the middle where it's going sideways, or it travels horizontally. That's the two kinds of things we're talking about. Increasing, decreasing, and constant. Here's the problem. Whether you're going uphill or downhill depends on which way you think you're moving. Like, if I start at this low spot, where 3 minus 8, and head up the graph to this high spot, at minus 2, 4.5, I was increasing, wasn't I? I was, right? I would travel vertically upward to go from the low spot to the high spot. But we call that section of the graph a decreasing graph, even though I can trace it in the increasing direction. What's going on there? It's that I've traveled the wrong way in terms of the x-axis. So these words, there's a relativity thing going on. You're increasing provided x is increasing and the y is also increasing. I feel like I'm saying that weakly. Here's a way to say it pretty succinctly. Always imagine walking to the right. That is, you're traveling, I think that's weird, my right is your left, I think, on the screen. So anyway, go in the direction where x is getting bigger. go in the direction of the positive x-axis. And if you're going in that direction, ask yourself, now on the graph, am I going up or down? If you're going up, that's an increasing graph. You see, it depends on which way you're moving along the x-axis, so watch for that. You could say that a whole lot of calculus is really about this concept, finding where graphs are increasing and where they're decreasing. Because, well, look what happens if you're at a spot like this one here, where you're increasing, and then after that you're decreasing. What does it mean to go from increasing to stop increasing and then start heading downhill? What kind of place are you at? It's the top of the hill, right? If you find yourself walking uphill and then a minute later you find yourself going downhill, you must have just passed the top of the hill. Well, we really like spots like that. We like to be able to identify the highest values of functions. Remember when we were doing the profit on the bike store? We wanted to find the highest spot on that curve, and it was visually obvious, so we could just do it by looking at the graph, but it's not always visually obvious. This is what calculus is about, is finding these values that give you the biggest profit, or the strongest airplane wing, or the largest of whatever quantity you're interested in. Sometimes we care about the smallest too. If it's costs, I like to minimize them. If it's profits, I like to maximize them. All right, so there's just some terminology you need to know about this stuff. I've already done the increasing, decreasing. Constant actually rarely comes up because you only see constancy if the graph is piecewise, and one of the pieces is just literally a constant value. But these other words I've just used, maximum and minimum, those are terminologies that we need to learn. So I think maximum makes sense. That's the highest point, max. I think minimum also makes sense. Do you notice that they have words in front of maximum and in front of minimum? So they talk about local maximum and local minimum. What does that mean? Well, local means out of all the points nearby, I'm the biggest, or I'm the smallest if I'm talking about a local minimum. So this is a question about a small locality, a locus of points that's near some particular value. Often you can have local maxima that are not the largest actual value overall. So they make a distinction between saying a local maximum and merely a maximum. I guess maybe I'll go back to that picture. This point right here, minus 2, 4.5, that's a local maximum. But it is not the highest point overall on the whole domain of this graph. We get up to that max, then we go downhill, but then, there's a steep uphill part, and do you see that we end up a little bit higher over here? So 5.5 is the maximum, 4.5 is a local maximum. There's a tendency, well, the convention is that we're referring to the y value when we say maximum. So it's 4.5. Actually, often we're more concerned with where does it happen versus what it literally is. In the example of the bike shop, you care about what production level should I set in order to get the maximum profit. What the actual maximum profit is that's what it is. You're just going to have to live with that. But attaining the best possible result depends more on the x coordinate that you set than the y. Still, the maximum here on this particular graph is 5.5, but there is a local maximum at 4.5. If you found the local maximum and thought that it continued to go downhill forever from there, you might stick with it, and you would be losing out a little bit. Slightly higher value available over here. Finally, one last thing about maximums and minimums is what I just said is wrong. The correct plural is to change it into an A on the end. So you have a maximum, but if you have more than one point that has that largest value, they are maxima. So the car named, is it Toyota? There's a car called a Maxima that's stealing a math term to get I guess that's a cool sounding name. So a minima is well, you can't say a minima, several minima exist. If you need to refer to a bunch of values that are all the same, that they achieve this the smallest value, there you say minima. Oh, finally, there's another word that you use if you want to sort of speak collectively about maxima and minima, which is extrema. Extreme values are either minima or maxima, and that turns out it's a word we use fairly often in calculus. Okay, that's it for section 1.6. If you want, I think it's probably good to go back through the book and at least make sure you look at the things in the gray boxes, highlight it and make sure you know the definitions of these technical terms we're using. All right, but that's it for today.